Oh, all right, welcome
Okay,
to this morning's CC Center for Computational Biomedicine's medicine seminars. My name is Tyrone Lee. I'm one of the senior software engineers here working with Ludwig. Uh, as some of you might know, I don't hold my alcohol well, asked Dr. Park. Unfortunately, there wasn't much on offer while at Posit Conference in 2023 in Chicago, which is this mass gathering of R developers, mostly using Posit packages. And Absalon, which has a really good booth location at that conference. Uh, and what they do is that they're primarily a consultant for a lot of our applications. They host very good, very good packages, applications for development, and I think that they also consulted for Boston HealthNet. At least when I heard from Adams' talk on dashboards and visualizations. So they did, however, offer a bar trivia with free drink tickets. So I managed to get in and caught the ear of Damien, the president at Absalon. And he introduced me to Ishmael, their sciences innovation lead. Uh, he is a biotechnology engineer, graduated from the Monterrey Institute of Technology and Higher Education in Monterrey, Mexico. Holds a master's degree in pharmaceutical sciences from Universidad Autónoma de Nuevo León, Mexico. He's currently pursuing a PhD at Jagiellonian University, the oldest in Poland, when the alumni was Copernicus, for instance, and that's located in Krakow, Poland. He's now
really?
serving as the life sciences innovation lead at Absalon. And we have a great chat for a couple of days at a conference right there on pharma research, our packages, and exciting developments such as AlphaFold. And he also shared this publisher, which I think was published while we were at the conference in molecular cancer. And I thought the story was interesting enough for a seminar. And thus, I invited him to share more about this. And along with him is someone that will cover some of the ML related developments at Absalon, Piotr Sua, a recent hire who was previously a pure mathematician, PhD in mathematics from MIT, with in 2020 with under Thomas Morka, Erdos number 4, and specializing in application of gauge theory. So since this year, he's been a machine learning engineer at Absalon, focusing on practical applications of machine learning models. So without further ado, take it away, gentlemen.
Thank you, Thyron. Thank you, everybody, for taking the time to attend to this seminar. The topic of the seminar is identifying protein crystals using machine learning, and me and my colleague Peter Subara will lead this presentation. So let's move forward. The topics for today are the crystallization in drug discovery. How is it done? Why is it useful? Why is it considered a bottleneck? We're gonna do a small demonstration about Shiny Molestar, this R package open source developed by Absalon as well. And we're gonna talk later about detecting crystals using machine learning. Now, thank you, Tyron, also for the introduction about our company, Absalon. Just to do a small recap, we do commercial projects in R Shiny machine learning. We do specialize in life sciences, and if you want to read more about everything that we do, please visit absalon.com. So let's start just discussing the basics. What are proteins? So these are biopolymers composed by chains of amino acids. They are involved in all aspects of life. They possess diverse roles, transporters, receptors, ligands, etc. So now I'm going to start talking about protein crystallization. When we perform the crystallization process, what we are looking for is for high quality crystals, such as the one that you're looking at the top right image. And once we have these crystals, what we can actually do is understand the molecular interactions of, for example, drugs and their targets. I'm gonna focus in this talk about the PDL1 and PAC65 receptor ligand complex. So what you can do when you understand those interactions is that you can perform directed drug discovery. You can as well perform enhanced enzymatic specificity. and of course, identify the hotspots that you can target with multiple drugs. So far, 90% of all the proteins that you can find in the World Protein Data Bank are obtained by X-ray crystallography. There are other methods as well, such as cryo-electron microscopy. This is a very recent technique, but so far, 90% are coming from X-ray. Now, let's talk a little bit about this important part, the costs and savings of having a protein crystal, having a protein ligand complex crystal as well. So when we're talking about bacterial crystals, costs, R&D costs can go up to $140,000. When we talk about human, then we talk about something around $450,000. But one of the most difficult type of proteins to crystallize are membrane proteins. There is a lot of effort to obtain such crystals, and the cost of R&D rise up to millions of dollars. So when we talk about regulatory submissions, for example, filing INDs for new drugs, then there are some reports that estimate that having the protein crystal can save up to $10 million, and this represents 50% reduction of R&D costs from target selection to the IND filings. However, all this process that I'm gonna show you in the next slides is an empirical process, although this technique has been in the research field for many, many years. So briefly, let's discuss the crystallization process. And we're gonna talk about here again about the PD-L1 protein. So let's say that first you select the target protein, in this case, PD-L1. You perform cloning and expression. For example, you can perform the cloning expression in E. coli bacteria. We have some specific bacteria for that, for example, BL21, etc. Top 10, the one for cloning. Those are the names that you usually find in the crystallization laboratory. Then you perform solubility and stability tests to check if the protein that you are producing in those systems is of high quality. For example, if the protein is folded. And once you check that, you can move forward with the large-scale purification. So large-scale purification, we're talking about maybe 10, 20 liters of medium to produce amounts for a single crystallization screening. The crystallization screening is something that we usually do with commercial kits. There are some companies that offer those and are successful. But however, you need to do, for example, multiple large-scale purifications to obtain a single crystal. And once you get a single crystal, most of the times it's not of high quality to produce a 3D structure that we usually need around 3 angstrom resolution to obtain the total structure of the protein. So we need to do crystal optimization. And once we have a nice crystal, we do data collection, structure determination, and having the 3D structure, for example, we can observe that using PyMol. So having that 3D structure, we can perform functional inferences, compare the structure with similar proteins. For example, you can compare human PD-L1 to mouse PD-L1. And in this way, you can understand why some drugs work or target specifically a protein rather than the other one. So there are some cases that some monoclonal antibodies target human PD-L1. However, they do not work or they do not bind to mouse PD-L1. So then you can understand how that is happening. Why is that happening? And as I previously mentioned, I want to focus here on membrane proteins. So to obtain one protein crystal, we need, in some occasions, several crystallographers and up to 20 years of this trial and error empirical process. So as I said, this X-ray crystallography technique has been around 200 years. And even though there are other techniques to obtain those 3D structures, X-ray crystallography remains the gold standard. There has been some technological advances, such as the robotic crystallography, but it still is a bottleneck. This is a manual intensive process. There is no theory or fundamental data on how to obtain a protein crystal for a new protein, and it continues to be empirical. So here I want to share a successful case study that me and my colleagues at the Jagiellonian University just shared a couple of months ago. And in this research paper that you're looking here, basically what we did is we obtained the macrocyclic peptide PAC65 and from a patent. And actually there was no information regarding how this peptide binds to the protein, how potent is this peptide. There was almost no information there. So we wanted to understand why this macrocyclic peptide was binding so in a very potent manner to the target PD-L1. And what we did first is to perform HTRF using CHO cells to observe the EC50 for this peptide. And we compared that to one of the FDA-approved monoclonal antibodies, atezolizumab. And what we found is that this peptide has a potency that is comparable to the monoclonal antibody atezolizumab. The PAC65 has EC50 of 0.58, and atezolizumab EC50 of 0.14 nanomolar. And EC50 just the half effective concentration of those molecules. So in comparison to previous macrocyclic peptides that have been published, we found around 600-fold increase of potency, which is really, really huge increase of the potency. And we went forward to understand how this was happening. So we decided to crystallize the structure of the peptide. And by having the crystal structure of this peptide together bound to the PD-L1 protein, we found the specific interactions between these two, ligand and protein. And we understood why the blockage was happening. And what we saw is that basically this peptide binds to the same region as the PD-1 protein, which is the natural binder to PD-L1. And this way we understood the mechanism of action and the mechanism of action of future macrocyclic peptides that could be developed, taking as a structural basis the PAC65. So by telling you this, I would like to talk a little bit about Shiny MolStar. So a Shiny MolStar is a totally open source R-Shiny wrapper for the MolStar software that you can already find if you go to the PDB, to the Protein Data Bank, you can already use MolStar there. It's already embedded in the website. So it's very useful, for example, to visualize a large-scale molecular data. So if you go to PDB and you select a protein of interest, you can play with it. You can analyze the interactions inside the protein or the interactions between protein and ligand. So what I'm gonna do here is just do a small demonstration of this totally open source package developed by Epsilon. And we decided to provide to the community, to the scientific community, this package totally open source because we think that this is a great form to help drug discovery. It's really important to understand, for example, those molecular interactions. So I'm gonna go ahead now and just demonstrate live the Shiny MolStar. So I'm gonna stop now the presentation for a second. And let me share MolStar. Just give me a second.
While it gets us up, any current questions from the audience? I can start taking them, or if you want, we can write and discuss in the chat while this screen's being shared.
Yeah, just give me a second. I need to in RStudio. I'm gonna run it. Perfect. Yeah, please feel free to ask any questions right now. I'm opening Moldstar. Oh, perfect. I found it. Yeah, so here is Shiny Moldstar. You are observing this. And usually when you will open it, what you can do is just go to the GitHub repository and copy all the code there into your RShiny um, window, RStudio window, and it will open always with this protein. However, you can go here and just delete it. And basically here in this PDB ID, we're gonna write the PDB ID for the PDL1 PAC65 PDL1. So here it is. As you can see, I'm playing around with the protein. At the top, you have the PDL1 sequence, and you can actually see here at the end that there is a his tag that, well, we ended not using it for the purification phase, but I'm gonna demonstrate here what you can visualize, but I'm gonna start by removing some of the unnecessary things, the ions, water, and this one. And at the top, I'm gonna go here to the ligand. And what I'm gonna show you right now is a water-mediated hydrogen bond formed by the tyrosine 1 from PAC65 and the serine 177 from the PDL1 protein. So it should be, it's this one here that we're observing. So we can see here the tyrosine 1. This is a hydrogen bond mediated by this water molecule here, and is together with this tyrosine, with this serine 117. So this is, of course, a small demonstration. You can find in the research article all the other interactions that we mentioned that are crucial to increase the potency of this macrocyclic peptide. And this works exactly as Moldstar. So every option that you will have in Moldstar, you have it here. You can play around and see, for example, the interactions within the protein itself. So it's very useful. Okay, so I'm gonna just go back to the presentation in a second. Perfect. So that was the demo, a very short demo. So I'm gonna go back to the topic of why to apply machine learning to identify protein crystals. And I want to focus on membrane proteins because those are the most difficult to crystallize. Just to say a little bit, to talk a bit about the numbers. So 25 of all proteins are membrane proteins. They represent more than 60% of drug targets. For example, if we talk about immune checkpoints, PD-1, PD-L1, CTLA-4, CD80, CD86, all of those are proteins that are receptors that are interconnected in, for example, cancer immunotherapy and oncology. So all of those are druggable targets. So something real interesting is that the unique structures of membrane proteins in the PDB, in the protein data bank, account only for 1% of all available unique high-resolution protein structures. So it's a very small number. And thousands of crystallization conditions are needed to obtain the crystal. So this is why it's crucial that if we're gonna be working 1 or 2 years and 2 crystallographers working on a single protein, then if we create a crystal, we simply cannot miss it. So with all this introduction of a successful case study, I want to now move forward with the topic of identifying protein crystals using machine learning that my colleague Piotr is going to talk about today. So Piotr, the floor is yours.
Thank you, Ismail. I hope you can see my presentation now, which is the same one, but from my side of share. Okay. Yeah, so thank you for this introduction and for telling us about your work, Ismail. And also, once again, thank you for the organizers for inviting us. I need to mention that I often visited Harvard as a PhD student down the river at MIT. I biked there for math seminars and classes, and not only that. So I'm glad to be at Harvard again, even if it's virtually. Without any further ado, let me introduce you to the problem there. So let's define what we want to do. So once we have an experimental setup where a protein is synthesized and it's put in various conditions, usually some automated robots very often make that, and then they produce images of the same protein in hundreds or even thousands of different conditions, possibly using various kits to get those proteins and get them crystallized. And roughly all the images could be classified into 4 distinct classes. They could have crystals. That's what interests us the most. They could have nothing. We call them clear then. They could have this precipitate condition that is not crystallization, but happens in different conditions, in different environments. But it's very often a result in such experiments. And you could also have other types of things happening, like just pieces of dust coming into the droplet, or things like that are hard to be classified. And you might want to keep track of those because they might, in some cases, sometimes crystals might be similar to those. You might want to distinguish those and maybe take a second look if you have such. But after all, we're really, really into detecting crystals, as Ismail said, and we do not want to miss any of them. And again, when you have hundreds or thousands of those images, you need human crystallographers. Well, a priori, you need human crystallographers to come and label them as being crystals or not. It's not the case in this image, but sometimes the crystals are very tiny. Sometimes you have a lot of precipitate, and then on their side, there is a small little crystal that a human might miss, especially if they're looking at hundreds, thousands of those, and they get tired, they're prone to errors. In the article that I'll mention in a moment, they say that humans agree on whether a picture is a crystal or not in roughly 93% of cases. So you see, that's very far from 100%. It's not obvious to human crystallographers whether some images are crystals or not. Thus, we'd like to automate it to get both just savings in costs and also increased precision. So people tried doing that, but basically the first real success, a huge success in identifying protein crystals came in 2018 when there was a large collaboration of research institutions, of researchers from various institutions, let's say, from the CCC, Collaborative Crystallization Center, Hauptmann Woodward Institute, GlaxoSmithKline, Universities of Buffalo, of York, Duke University, and researchers from Google as well. So what did they do? They wanted to get this 4-way classification of images coming from those crystallization experiments to identify whether something is a crystal, a precipitate, is it a clear picture without anything special, or is it something else, something special happening. Maybe there's not even a droplet at all there. So the first thing they did is they gathered a huge data set of roughly 450,000 images, gathered from 5 sources: the CCC, HWI, GSK, which were part of the collaboration, but also from Merck and Boston Myers Squibb. This dataset, which we will refer to as the Marco dataset, and by the way, Marco stands for Machine Recognition of Crystallization Outcomes. That's how they called it. So I will call their dataset the Marco dataset, and the model they prepared, a Marco model. So what did they get with the Marco model? Where they succeeded in outperforming human crystallographers, at least to their knowledge, on the task of identifying crystals. So their model that they trained on the test set, which is a part of this Marco dataset, it achieves an accuracy of 93.5%, which is distinguishing whether the picture is of a crystal, it's a clear picture, a precipitate, or something else. When we restrict this to just asking whether whether an image contains a crystal or not, of course, the accuracy is a bit better. It's 97.7%. So this is the accuracy on the task of identifying whether there is a crystal in an image or not. So, very impressive, and these are great results, actually. They did very good work, especially preparing the data set, which is invaluable. But their model has a few shortcomings. So firstly, it exhibits poor generalization qualities. Let me explain what I mean by that. So firstly, one of the institutions that contributed images to this Marco dataset was the CCC, the Collaborative Crystallization Center. And if you look, if you take Marco model, the Marco model, and evaluate it only on the images from the CCC dataset, then it achieves only 85.2% accuracy, which is much less than 93.5%, which means the model fits very well to some other datasets that are bigger, but maybe not necessarily this one, which is much smaller than the other ones. If I remember well, there were roughly on the order of 20,000 images from CCC in the training set of this model. So that's one thing. Even on the data that it was trained on, it doesn't get super accuracy. But then the researchers from the same institution that I mentioned, the CCC, Collaborative Crystallization Center, that is Rosa Watkins and Newman, earlier this year, they published a new data set of images from the very same institution, but prepared with completely a new experimental setup, with new tools that they use to produce the crystallization. So the images look different from the ones, a bit different from the ones that are in Marco. And on this new data set, well, actually, there are two of them. One is just a regular, one is a data set containing, let's call them regular images. They call it a visual data set. And the other one contains ultraviolet images. Let's call it the UV dataset. So on these two datasets, Markov fares worse as well. So the Markov model on the visual dataset, it achieves 82.5% accuracy, which is decent, but it already is much more prone to missing crystals than when evaluated on the other institutions that the Markov dataset has. Also on the UV dataset, the Markov model accuracy drops to 49%. So that's already quite poor performance. And this follows because this dataset it looks completely different. The UV pictures are very much different from anything that is in the Markov dataset. So then if you have an experiment when you do want to detect crystals, if your experimental setup produces images that are different in various ways, like in the shape of the droplet that is formed, in the shape of the crystals that are formed, maybe even in the colors that are in the image, then you can surely expect that Markov does not achieve 93.5% accuracy on your data. So, but then you could say, okay, let's take Markov and retrain it using the original Markov dataset and some data that you provide. That's going to be a bit cumbersome because the way that the researchers that made Markov did it, they used 40 GPU days to train the model. So they used NVIDIA K80, if I remember well the name, but nowadays you would use, for example, NVIDIA T-Force, and if you train their model on an NVIDIA T4, which is of similar computing power, it would take you over a month to train it. That's quite a lot. So with Andrew Cusick from Epsilon, we took up the challenge of improving on this situation. And let's see how we did it. So firstly, we took a newer, more modern model architecture for visual tasks. We used VIT, Visual Transformer. And by the way, you might have heard the word transformer in the context of large language models. So indeed, the similar architecture of transformers is underlying the VIT model, the Visual Transformer, which was developed by Google. Secondly, we leveraged transfer learning. So the authors of the Markov model, they just started the training from scratch. They took an Inception v3 architecture and they just trained the model using the data they had with crystallization outcomes. What we did, which we took a version of it that has already been trained on a vast data set of ImageNet. That is, the model was already trained to distinguish among thousands of classes. And it was trained on a data set of hundreds of millions of images in the ImageNet. And it could already distinguish cats from dogs, from cows, from buildings, from windows, and so on. Definitely, it couldn't distinguish protein crystals from precipitates, for example. But that's what we did. That's what we did. If we took this model that was already trained on other data and we further trained it to detect, to distinguish between crystals, precipitates, clear pictures, and others. Moreover, actually, the most important task is to distinguish crystals from anything else. So we then further fine-tuned the model to identify just crystals. So for the task of binary classification, whether something is a crystal or not. It's a bit simpler, and it also makes it a bit simpler for the model to learn, especially if it encounters mislabeled images, because it's not very much clear for many of those images how to label them. So surely not all of the data in the Markov dataset is labeled perfectly. If we reduce the noise, we can hope for a better outcome as well. And these are the results that we get for this. So our model, when trained for distinguishing the 4 classes I mentioned, it achieves just slightly better accuracy than Markov, that is 94%. Then when we fine-tuned it to just classifying crystals, just identifying crystals and not crystals, and we made it, we set the threshold for detection so that it matches the precision of Markov model. That is, it has the same number of false negatives on the same data set. So it matched the precision of Markov, but the recall, which is the quotient between the number of correctly identified crystals and the number of all crystals in the data set. The recall is higher. So what does it mean? It means that the original model, the Markov model, it misses 11.1% of things labeled as crystals. And our model misses only 7.6% of those things. So in terms of missed crystals, our model misses roughly 30% fewer crystals with the same precision. So you get the same number of things that are not crystals, that are labeled as crystals, but fewer crystals that are missed by your model. Moreover, thanks to our approach, our model is trained in just 1 day on a single GPU. So that's much faster, and you can readily apply it to data from any other lab. Maybe I could take some questions now if you have any before I go into the second step.
For the binary classification fine-tuning, that was a supervised approach. You're just putting in stuff that you already labeled or have a defined set of crystals for that fine-tuning set.
Absolutely. We did only supervised learning using the data available in the Markov dataset.
Okay. I think we're good on questions, I think.
Okay. Anybody else? Okay, let's go forward then. So then a very realistic scenario is that if you come from a lab that makes those crystallization experiments, your setup probably differs from the setups that were used in generating the Markov dataset. So how can we make a model that also works well for your data? Well, we first take this data that has been used to train the Markov model. We take the Markov dataset and we train the model on this known data from these 5 sources. We train it to do either the 4 class or the binary classification. And then we use a modern fine-tuning technique to fine-tune it further to the new data set that is coming. And just to give a few words on what we do, we use the LoRa technique, which is a shorthand for low rank approximation. technique. So it has been used to very successfully fine-tune large language models. It works very well with transformer architectures. And guess what? We did use a transformer architecture here. So we can use LoRa here to fine-tune our model, even using very small data sets, without destroying it by overfitting to the small number of examples that are provided. So I mentioned the CCC, researchers from CCC prepared these two new data sets that are outside of the Markov data set. And when you take the Markov model, or when you take the Markov model and apply it to the VIS, the visual data set, out of the box, it gives you the accuracy of 90.7%. Mind you, now I'm just giving you the accuracy of detecting crystals. So I'm focusing on binary classification right now. Okay, so for binary classification, Markov on this data set gives the accuracy of 90.7%. And our pre-trained model fares a bit worse. It gives the accuracy of 86.1%. But what we can do is, if we take just 60 crystal images from this new data set, we also add 60 images of clear images, 60 images of precipitates, and 60 images of others, just other things happening in the experiment. But crystals are the rare ones. So if you can get 60 images of crystals, you can surely get 60 images from each other class. So with that data, when we fine-tune our model to this data, we get 92.9% accuracy, which is already better than the Markov accuracy on this data set. And then the full data set here contains at least the part that we took for training, not the part that we set aside for testing. The part that we took for training, it contained 2007 images of crystals. And with that many images of crystals, we already achieved the accuracy of 95.7%, which is already very high. And 2000 images of crystals it is quite a lot, but it is still much less, way less than the images of crystals that were in the Markov dataset. Most of the institutions that provided data for the Markov dataset, they provided over 10,000 images of crystals each. So 2000 is much less, much fewer. So that's great. So we expect that for any kind of data set that is produced using a different setup, we should have a similar relationship. And for example, when we look at the UV data set, it seems it's much harder for the models to understand, as out of the box, Markov gets just 70, almost 76% accuracy on this data set. Actually, here, our pre-trained model, without any fine-tuning to this data set, fares better than Markov. So that's good. But we can do better. Even with just 60 images of crystals, we get almost 82% accuracy. And with the full data set, at least the trained part of the data set that is provided, we get 92% accuracy, which is much more than Markov's result out of the box. So to sum up, we train a model on the Markov dataset, obtaining the same precision but better recall. That is, we're missing 30% fewer crystals that the Marco misses. And then we only do this using 1/40 of the GPU power. We can do this in one day. Just for tomorrow, it can be ready. Moreover, our model is very easy to fine-tune on new data, and it does it very efficiently. If you give us 2,000 images of crystals, you get as much as 92 to 96% accuracy. If you give us fewer, like 60 images of crystals, we still can beat Marco used, without further modifications. And now I give the floor to Ismail.
Thank you, Piotr. So, as a summary of the first section, the introduction, I would like to go back and mention once again that protein crystallization is still a bottleneck in drug discovery. A lot of people, a lot of research groups around the world are trying to find new ways to optimize this. All of this is a manual process that takes and requires a lot of crystallographers. And the most important part here that we want to mention is that missing a single crystal could halt a significant discovery. So with that, Piotr, can you move forward, please? With that, we would like to say thank you for attending. Here are the QR codes for our LinkedIn profiles if you want to connect with us, and also to read more about all what we are doing regarding life sciences at Upsilon. Thank you so much. And we're open for questions, of course.
Thank you so much. Thank you so much, Piotr, and thank you so much, Ismail. Ismail, this has been an interesting talk. So for this new fine-tuned protein crystallization, it's an image classification model. So is Epsilon providing the scaffold for this to run inference, or are you interested eventually in trying to put up the weights on Hugging Faces or something?
That's a very good question. Actually, this has been a very recent research and we definitely don't have answers to that yet. It would be great, firstly, before we do anything like that, to get in touch with some lab and actually provide the lab with this model, let us fine-tune it to their data and see if it is actually good for this other data set. Of course, it already worked for these visual and UV data sets, but it would be great to confirm with more labs. And then I guess Jędrzej is here. Maybe he could say something about it.
Yes, so hi everyone, my name is Jędrzej and I'm the head of AI at Epsilon. So what I would add to that, to what Piotr said, is that indeed if any of you has access to such data set and would like to try this model or this method on their data, feel free to reach out to us and we'll be happy to collaborate to basically help you do this. Answering the question of like long-term, is this going to be open sourced or is it going to be a commercial offering? We are in general a commercial company and we do provide in particular machine learning services. So of course we are interested in particular in commercial projects around this topic. However, as Ismail already showed during this presentation today, right, the Shiny Molestar is a package we developed and then open sourced completely. So we are kind of open to open source, right? So we have published research papers on different topics in machine learning as well, and we'll be more than happy to, for example, work on a project in a kind of more academic / research setup, and then which, for example, leads to a paper or just leads to an important advancement in your research lab. So it really depends on the setup. So feel free to reach out, or if you know someone and you can direct us or connect us with them who could be interested, then please do so.
Okay, we'll take questions. I guess Robert first. Would you like to go?
I think Ludwig was ahead of me.
Okay, Ludwig.
Thanks. Thanks for a great talk, Ismail and Piotr. Two questions from my side. So thanks for this demo of Shiny Molestar. Ismail, I was wondering, is there some integration with AlphaFold already? It seems like it's primarily at this point a PDB viewer, right? I wonder whether maybe some integration, you know, like with these quality scores that come out of AlphaFold, PTM, or pairwise alignment, or error, or PLDD, could be kind of like provided, maybe even that you select certain parts of like your pairwise alignment error, and you kind of like get this highlighted on your structure or something like this could provide for some nice additions. And then the other piece, my other question is, so I'm quite curious what you guys are doing over there at Epsilon. I have read a couple of things. I also saw some bioconductor posts. It would be very interesting for us if you could say a couple of more words about like your mission, about your scope, what kind of apps you are developing. I think that would be very interesting. Thanks.
Yeah, so I can I can go ahead and answer the first thing about integrating AlphaFold with Shiny Molestar. We actually already integrated AlphaFold into Shiny Molestar, so you can utilize AlphaFold if you copy some chunk of code into the RStudio window, of course, and you can visualize proteins that are predicted by AlphaFold. However, I think we could enhance that part definitely, as you say, like for example, you can select a region and then mutate it and use AlphaFold to see how that looks, and check if there are some differences. So yeah, that's a good point, and we will definitely look into that. We are still working on Shiny Molestar, and it's one of the life sciences packages that we have so far. So yeah, we wanna take into account this point and continue moving forward with the integration of AlphaFold, definitely. And regarding the second point of what we do at Epsilon, well, as I mentioned, the mission here is to utilize cutting edge technology to improve human life, right? We want to experiment with as many technologies as possible. We are currently focusing on R-Shiny and artificial intelligence for life sciences. We know and we understand that working on life sciences can have definitely a huge impact in human life and increasing quality of life. So that's one of the things we focus on, right? And we love contributing to open source. We definitely worked a lot on Shiny Molestar. We have also Shiny Ghost-Link for genomics visualization. So Molestar and Ghost-Link per se are already very famous, I will say. So we decided to take those and integrate it into Shiny because, as you know, Shiny is mostly open source. There are many packages as well for R&D. So integrating this into Shiny was a really cool idea that we had, and yeah, so we want to continue having projects that could enhance drug discovery and reduce the submission time to the FDA, for example, for INDs or NDAs filings, and reduce the cost in overall cost of drug discovery and development.
And maybe if I can add to that, if you're asking about like how do we arrange projects, like what types of projects do we work on, then as we mentioned, we are a commercial company, right? A private scale-up, it's called. We're around 100 people now. And we're indeed running mostly commercial projects for example, in Shiny space, this is mostly pharma. So basically companies which use heavy statistics and heavy analysis, statistical analysis in their data science departments, because this is often done in R, and then visualizations of it or building dashboards, interacting with the data And the summary is mostly done with Shiny. So that's why we're kind of mostly, I would say, located in this space, but also some others where heavy statistics is needed. And then in terms of machine learning, we mostly do computer vision, again, typically long-term research and development projects concerning some new type of data with some new tasks for commercial clients. But in both departments, we do quite a lot of open source and kind of like academic research, and then either publish results in terms of open source packages or basically knowledge sharing in blog posts or scientific papers.
Go ahead, Robert.
Yeah, great talk. I'm sorry if I missed it in the presentation, but you sort of started off by saying how different sort of bacterial proteins from human proteins from membrane-bound proteins were, but then at the end you didn't really talk about, you know, error rates sort of divided into those different types of proteins, or so if you could give any insight on that, right? Some must be much easier to predict than others. And then are there particular structures of the proteins that you know, are able to do well? And then maybe just obviously it's sort of like the unstructured regions of proteins. What do you do there? Do you sort of just identify those and leave them out of your calculations, or are they sort of left in? And I guess it'd be interesting to know how you're thinking about that.
Yeah, well, certainly there are some differences between you know, expressing human proteins in bacterial systems, basically because, of course, human proteins have other types of modifications that are difficult to replicate in bacterial systems. So you need to use other mammalian expressions, such as CSO is something that we use, which is really, really expensive. Half-liter medium, I don't know, costs like 2,000 euros or something like that. So when we have a crystal structure and we have like a non-structured region, once we got the crystal, we send it to the synchrotron and we have a non-structured region. If this structured region is not crucial to understand protein ligand interactions, then there is not a problem. We can leave it like that. But of course, we need to focus on for example, there are some statistics before you submit the PDB structure, the structure to PDB. So you need to check that. But once again, it's possible to submit such proteins where some regions are not well defined in the 3D electron density map. And if there is a huge problem with those, then basically we need to go back to the first step, to the second step, which is the cloning and expression. So what we do is basically modify that region, adding an extra amino acid or removing an amino acid, and then we can further study that. But as you will understand, doing that takes many months of work. There are some commercial kits to do cloning and expression right now, but it needs to be done manually and by experts mostly. But talking about statistics of how many proteins we found unstructured, I actually don't have those numbers right now. I'm sorry.
Thanks.
No problem.
Anyone else? Okay, I think we're about good to wrap up. We're about 2 minutes over. Thank you so much to the team at Absalon, Ismail, Piotr, Jerzy. It's been a pleasure talking with you, and thank you so much for coming, and hope to have a great rest of the week. We'll be in touch.
Thanks.
Thank you, Tyron. Thank you, everyone.
Thank you, guys.